Maybe. So good morning once again. Welcome you to another session of ME324. So last week we discussed how we discussed the derivation behind the constant strain triangular elements, and we developed the equations behind this, and we also applied it in an example and calculated or tried to see how the results tend to improve or the performance of let's say a hand calculation when a certain amount of very limited amount of constant triangular elements were applied, because we already we are already doing hand calculations, and we also resort to, or we also came to the conclusion that it is quite obvious and it's quite necessary to use the help of computers or computer calculator to perform computational use the help of a computer to perform these computations, because the size of the matrices and the computations tend to be cumbersome. We also discussed certain limitations the element when the CST element is applied in finite element simulations, because especially when we think of bending problems, the application of CST elements tend to provide a more rigid model than what is expected in reality, because we assume a constant strain within this element. But of course, by reducing the mesh size or increasing the number of elements, the results could be satisfactorily improved. But nevertheless, since when we think of applications where the stress variations are quite, let's say, drastic, or there's a certain amount of stress variation within a certain specific range, then we need to resort to more elegant solutions, something like using another type of element which can incorporate this stress variation for a certain elemental part or certain region of the model is quite important. Within this, in this context, we also briefly talked about another element which we call as a linear strain triangular element, or in short we call it LST. As the name denote, the strain within this element is assumed to be constant. In the previous element type which we discussed in the CST element, the strain was again constant, but in the linear strain triangular element, the variation of the strain is not constant, of course, it's linear. So that's what the name denotes. So these LST elements have been incorporated in the commonly used FEM codes, and of course there's a trade-off when we think in terms of the CST element and the LST element. Of course, there are certain while there are certain improvements to incorporate the variation of the linear strain or variation of the strain in a linear manner, it comes at a computational cost. So if we think in terms of, let's say, the CST element, constant strain triangular element, and the LST element, which we are going to focus today, in the CST element, if you can recollect, there were only 3 nodes which we considered, which are located at the apex of the nodes, of course, at the very ends of the triangles. So each node had 2 degrees of freedom. So 3 nodes, and all in all, if we consider it the 2-dimension, of course, XY Cartesian coordinate system, where the displacements in x direction is given by u and displacements in y direction is given by v, we had to consider 6 degrees of freedom, that is 2 degrees of freedom per node times 3, that is 6 degrees of freedom. So now in the case of LST, linear strain triangular element, the problem becomes further complicated. The problem further complicates, and you will realize as to why we require the help of a computer to solve such type of problems. So in the case of LST, linear strain triangular element, we now have, in addition to the 3 nodes located at the very end of the triangle, there are also mid-side nodes at the very middle of the certain edge. Let's call it . So there are altogether 6 nodes. Each node has 2 degrees of freedom, just like in the previous case. So altogether 6 degrees of freedom. So what can you think about the stiffness matrix of this LST element? The stiffness matrices applied when we talk about LST elements. The rank or the size of the element drastically increases. So from 6 by 6 from the which was present for the CST elements. Now we move on to or discuss the rank of the matrix having elements or have the size of 12 by 12. 6 nodes, each node has 2 degrees of freedom. So 12 by 12 matrices have to be tackled or developed when we talk about stiffness matrices in connection with the LST elements. So just before we move on, I will just show you as to, so it's the same notation, of course. Each node has, of course, 2 displacement functions. So the displacements in the x directions are given by the displacement functions u1, u2, u3. u6, and the displacements in the y directions are given by v. Yep. So once we define the n nodes, that is node number 1, 2, 3, the computer programs can automatically calculate the mid-side nodes based on the geometric relationships. So in the LST elements, the computer will calculate the mid-side nodes for you. But as you can see, now we are dealing with a more complicated problem. Complicated in the sense we have more number of nodes. And also when we talk about the shape function, since we have a mid-side node, also you can see that additional mid-side nodes. Now we are not using shape functions having linear shape functions, but we are now considering to go increase the order of the system, or the order of the displacement function, meaning we will be using quadratic functions to describe the displacement within this element, of course. So the onset itself, I would like to tell that the derivation of the LST, the stiffness matrix of the LST element is very much the same as the CST element, the same procedures. So I will just highlight the important steps, and we will be quickly working on an problem just to get the hang of it. I will not go into very much of details because we went into the derivation of the CST element, and you are quite familiar with this, and we have already gone into the different steps. Here I will just only highlight the important steps and the equations and directly use it to solve an example. So by looking at a certain example, the process, the derivation of, or the equations behind the LST element, which we will apply, will be quite, you will be able to get quite familiarized with the set of equations and with the mathematics behind the LST elements. Because the reason is, eventually, since we have large number of degrees of freedom, it will be hard to perform hand calculations. So eventually you will be using a software or some kind of a computer program to do the calculations. So the motivation or the objective of this lesson is for you to get an understanding or feeling as to what is really happening when you really apply these elements in a software, when you are using LST elements or CST elements in a software. What is really happening behind this algorithm? So if you have a feeling for this, if you have a sense of this, then you will be able to tackle very complex problems, and you will be able to use your know-how or intuition to in cases where there are certain situations which require a judgment from the programmer or from the modeler. So this is what we are practicing as engineers. The more experienced you are, you will be able to use that experience into developing and finding the solution in the finite element model. So in the latter part, if time permits, of course, we will be discussing some of the important practical aspects regarding developing a finite element model, and of course solving a finite element problem. I will also provide some additional material because during a lecture it's really hard to cover such a vast contents. There are different aspects which you can consider when you are modeling a system, and when you are thinking in terms of improving a certain model. So I will provide you some additional reading material. You can go through them and also apply the knowledge which you gain in the lab classes in order to improve the results of your finite element simulations. Okay, having said that, let's focus back again on the LST elements. So the LST element has 6 nodes. So 12 degrees of freedom altogether. So the unknown displacements can be described by a matrix, column matrix, which we can write down for the 6, of course, 6 nodes. And each node has 2 degrees of freedom. So displacements of each node will have an x component as well as a y component. So you see, we have, when we talk about the displacement function, we have a column matrix, a 1 by 12 column matrix, sorry, a 12 by 1 column matrix. When we talk about the displacement functions for displacements in connection with this element. So the next important step is, so the first step, as usual in the previous sections also, we selected the element type. So these steps are quite important. I will most probably ask also during the examinations, maybe these, because these are the really important steps which you have to or follow when you tackle a FEM problem. So step one is the selection of the element, which you have already done, and in the step two, what do we have to do? Step two, the idea behind step two is to select a displacement function to describe the nodal displacements. Yeah. So as in the previous case, that is when we considered a CST element, we selected a linear polynomial, a linear displacement function, but since we also include a mid-side node, and when we think in terms of the compatibility conditions, it's more logical to describe the displacements of each side using a parabolic function. So meaning we will be selecting a quadratic displacement function for this describing the displacements in each element. So we're using a quadratic function. So the x, or the displacements in the x direction, is a function of again x and y. And if you can recollect, since we have 12 degrees of freedom, we will have two functions with 12 unknowns, which we will have to calculate to solve the problem. So since we are applying a quadratic function, we can define the quadratic function like this: a1, a2, x, a3, y, a4, x squared, a5, x and y, and a6, obviously, y squared. Similarly, we can come up with a function for describing the displacements in the y direction: a7, a8, a9 is a function of y, a10 is a function of x squared, x and y. Okay, so we have used quadratic functions to describe the displacements of the of each node. So just to recap, maybe, or before we move on to the, let's say, the derivation or the main points of deriving an LST, the stiffness matrix for an LST element, just to recollect about the Pascal triangle. Of course, whenever there are, let's say, if I do, let's say, whenever we have a constant term, or if we are thinking in terms of a constant shape function or constant displacement function, we have only one term. Of course, the degree of the polynomial is 0. Of course, number of terms, let's say. And of course, the element, this case, it won't triangle that we consider. So let's say in the case of a CST element, constant train triangular element, we have used a linear polynomial function So meaning the degree of the polynomial function is 3, and there are 3 number of terms to describe this polynomial or linear function. And the problem gets slightly complicated when we're increasing the number of degrees of freedom, that is in the LST element, we considered a quadratic function. So the number of degrees, of course, 2. There are 6 number of terms which we would have to identify, of course, and each term, of course, if you think in terms of a linear term, we have an x, let's say y. Of course, here we have a constant. Let me use the color for that to be clear. For a constant term, we have only one, of course, one term, and whenever we have a linear function, we have 2 terms, a constant term, and of course another 2 terms, and a quadratic function is always comes with such type of terms. So we would have to consider there would be 6 components if we consider the parallel triangle. So 1, 2, 3, 4, 5, 6. Yeah. So there will be 3 elements, 1, 2, and 3, when we talk about a linear function. And when we talk about, let's say, quadratic function, there will be 6 elements altogether. Similarly, when we talk about functions or quadrilateral strain elements, of course, we will have then extra terms, cubic terms coming into play. Altogether, we have 10 terms. 10 terms. The degree is 3. These are cubic polynomials. Usually in QST elements, there are 2 mid-side nodes, not 1 mid-side node, but 2 mid-side nodes. And in addition, there is a node at the centroid. So these are different types of elements. Depending on the nature of the problem, you would have to use the most appropriate element to describe your problem effectively. So what I wanted to highlight from this is that whenever we use more sophisticated elements, the number of degrees tend to increase, and we can also use having higher degrees, high degree shape functions, high order polynomials to describe the displacements accurately, especially when there are rapid changes of loads, rapid changes of strains, and changing of the material, of course, changing of the boundary conditions. In such cases, higher order shape functions are necessary to capture or to accurately describe the displacement at such locations. So the displacements described in equation 6.1 to 1.2 can be written down in the form of a matrix if we take away the constants and, of course, the coefficients. separately, if we separate the coefficients and the values of the coordinate values, which we can the variables which where we can represent them in the form of a matrix. We would like to express u and v, which we can conveniently separate into different, let's say, we will be using a column matrix to take out to separate all the exponents. There will be 12 exponents. So this is simply, I have represented the equation 6.1.2. These are the two equations in the form of a matrix, nothing new. So we can write down the exponents so that if we do the matrix manipulation, you will end up getting the same equations as in the previous case. 1, 2, 3. So I had to squeeze this up a bit. 1, 2, 3. So the same number of terms would appear from the sixth element, because when we talk about the v, or the displacement in the y direction is independent of the constants from a1 to a7. So we can represent this equation as the displacement. Of course, the displacement function is given by a so-called M matrix. Let's call it M hashtag, be consistent, the terminologies, and A. So this A matrix, the M matrix is what we get separated when we separate the coefficients from the variables. So the coefficients from A1 to A12 can be calculated by substituting the coordinates in the following manner. So we are interested in calculating, let's say, u1 and u2. Of course, let me write it like this. So we know we expand our function. So if we substitute the coordinate value for in the equation 6.1.3, what we would get is, we have 12, of course, from u1, u2 up to u6, and from v1, v2 up to v6, we have defined displacement functions. And now I have to make use of this M hashtag matrix, which is, let's say, for one element I will write down. So when we talk about u1, we have to substitute the coordinates for the first node, that is x1 and y1 are the coordinates of the first node. So it would be x1, y1. So this equation, now what we're doing is we are simply using equation 6.1.3 and substituting the coordinates. So u1 will become x1 y1, x1 squared, x1 y1, y1 squared, 2, 2, 3, 4, 5, 6. Similarly, you can write down the rest. So up to v6, u6 rather, and from v1 onwards, the first three elements would be, first 6 elements would be 0, and of course, this will repeat now. So y1, x1 squared, x1 y1. Is it clear, everyone? I hope we are on the same page. And of course, when you do with the completion of the matrix, which has to be multiplied with the A matrix, which I will write here because I ran out of room. A1, A2 up to A6, and it will go up to A12. So now what we are interested is, in order to solve the displacement function, we are interested in finding the coefficients, that is A values of this matrix. So in order to find the A values of this matrix, I will write this equation as 6.1.5. What we can do is we can simply obtain the inverse or multiply this equation 6.1.5 both sides with the inverse of this M hashtag matrix. Okay, so we are interested in obtaining these coefficients A1 to A, let's say 12. What we do is we simply multiply the left hand side, of course the right hand side, by the inverse of this this matrix. So obviously what you would end up is getting where the same matrix, of course. I will just write an arrow here just to save some time. The same matrix multiplied by of course the inverse of this matrix, which is multiplied by now the displacement functions u1, u2 v6, u6, v1 to v6. Yeah, so what is this equation? In the abbreviated form, we can say this: the coefficients are obtained by, let's call this an X inverse matrix because we substitute the values already, and which is multiplied by the displacement matrix here. So we know that the X inverse matrix is a 12 by 12 matrix. So it's really hard to perform an inverse of a matrix of this rank. So you would have to resolve to a certain algorithm or use the help of the computer to calculate the inverse of such a matrix. So as I mentioned before, I will only highlight the important steps here and which is required to solving kind of like to get a feeling for what we are trying to do when we solve a problem with an LSD element. So at this point, we have defined the coefficients using an inverse matrix substituted with the coordinates as well as the displacement function. So now we can write down, we can use, of course, the equation 6.1.7 here and 6.1.4, these two equations, 6.1.4 and 1.7, 614 and 617, we can obtain this expression for the general displacements, or the we can obtain the expression for the shape functions, which describes, of course, the nodal degrees of freedom. So what we can write down is, if you do the substitution, we can write down is as the shape, the displacement function, of course, the shape functions multiplied by the displacement vector, and where the displacement vector, displacement functions can be defined as using the terminologies which we used in the previous session. Yeah, so I have these are different terminologies. I have done different substitution. I have only used equation 6.1.7 and 6.1.4 and obtain just a general description for describing the displacement using the shape functions. Yeah, so you will see where I am getting at when we go on with the example. So for the time being, just try to graph these important equations that we will be using to solve the problem. So the next step, of course, is after we selected the displacement function, which we did now, and already expressed in terms of the different matrices which we calculated. M star matrix is nothing but the matrix, of course, I have given here. X inverse matrix is the inverse of this matrix which I have provided here. Right. So with the help of this, we obtain to get the displacement function. So in the step 3, what we do is we apply the stress-strain relationships, and of course strain displacement relationships into the problem. So we are interested in defining the strain within the element, and for this we define 3 terms: strain in X direction, strain in Y direction, and the rotation, of course, shear strain. The XY plane, which we can conveniently describe by using the derivatives of the displacement functions. So I will directly use this now. You can go back and refer to this material visually. Just like in the previous session, which we used to derive the CST element, we will be using the different the derivations. So the derivations of the displacement function with respect to X, Y, and of course the combination of these two will yield us the strains as well as the rotations when we think of in terms of the LST element. So once we do the derivation, or if we look at equation 6.1.3, that is this equation, if you consider this equation and do the derivation, so what we're interested in is calculating the of course the strains, and for this we have to obtain the derivation first, derivative of u with respect to X and derivative of v with respect to Y, and with the help of these functions, of course, using the function you can obtain the derivatives. And if you do the derivations correctly, your strains can be expressed using, let's say, this type of a matrix. On the left hand side we have the coefficients, so we do the derivation, of course, and we take the derivative and separate the coefficients. This is what we have done in this step. So 0. So similarly, what you would get is so you can perform the derivation and check whether you have got the correct results here. I will directly write just to save time. So we can observe that the strain of this with the equation, let's say 6.1.11 describes, is linear. That is what we call it, a linear strain triangle. So we can express this strain within this element using, let's call it the M matrix, M prime, the A matrix. All right. So we can substitute this equation again in the 1.6.1.6 and find the substitute the corresponding A coefficients, which we have found the coefficients, into 6.1.12 again, and describe the nodal displacement as using a B matrix and displacement matrix, just like in the previous session that we did. So what we have done is we have substituted equation 6.1.6 and found the A values, and you have used the corresponding coefficients into equation 6.1.12. So the nodal displacements can be described, or the strains can be described using the B function, which is a function which includes it's a function of the coordinate systems, and of course the displacement function here. So here the B function is a function of variables x and y. So this is a function of, let's say, just like in the previous case, it was a function of x, y, and certain constant terms. So this is a function of x and y, and of course which are functions of which meaning this will have include the coordinates from a1 x1 y1 to a6 x6 y6. Yeah. So once we know the stresses, the corresponding strains can be calculated by, so let's call this the B matrix, which is, so you'd have to bear up with me with these equations. Take your time, maybe after the lecture, to go through this set of equations, how we have connected different equations. I want to put some basic foundation before we go to the example, because we will be using these equations in the example. That's what. So it's the same. What I'm reiterating is it's the same procedure that we followed in the previous step. That's what I am quickly browsing through these different sections. So prime. So the next important thing is we are interested in calculating the stresses within the element. Of course, the stresses in the x direction, y direction, and the shear stress in the xy direction is what we are interested in. For this, we include the material properties and also the Poisson's ratios and the knowledge of elasticity. If you can recollect, the constitutive matrix, which we discussed in the previous session, has to be multiplied by the strain matrix, which we just calculated above, or which we just defined above. So all in all, this equation would be D, and since strain equation can be expressed in terms of B times D, can write the complete stress equation using the D matrix and B matrix. So for plane stress conditions and for plane strain conditions, there are different forms of the constitutive matrix or D matrix which we applied and which we discussed. According to the problem, you can use the correct D matrix and apply in the problem accordingly. And you can see the stresses are now, they are linear functions of X and Y coordinates, because B matrix now is a function of X and Y coordinate. So in order to derive the element stiffness matrix in step number 4, what we have to do is the element stiffness matrix would now be given by obtaining the transpose of the B matrix, the D matrix, and of course B matrix, which has to be integrated over the volume. It's a volume integral, which is quite hard to calculate by hand, of course. And the element stiffness matrix can be obtained using by performing the integration. And here we have to perform the integration because this B matrix is a function of X and also Y, as it was given in the previous section. So one last equation, of course, maybe two equations before I show what is this B matrix that we're talking about, which we introduced here. Of course, in equation 6.1.14, if you resolve this equation and rearrange the terms or separate the terms, we can define the B matrix to be nothing but a function of the area. And we have now 12 terms. Let's introduce certain terms. We call it beta. Beta 1, 0, 0, gamma 1. So beta 2, 0. So this same form would repeat 6 times. So I will not write down all these 6 terms, but beta and gamma, what we have done is we have simply rearranged the use the coordinate system and rearrange the equations. So these beta and gamma are nothing but it did not drop from the sky. They are functions of X and Y, just like in the previous derivation which you followed. So beta and gamma are nothing but they are functions of X and Y. Okay, meaning they are functions of X and Y as well as nodal coordinates, which was illustrated also in the previous section. So now we have laid down most of the, let's say, important concepts of equation, at least, which we'll be using to tackle a certain example. And when we go through the example, it will be more clear to you as to what different steps. It is nothing but the same concept that we are applying in the previous, just like in the previous section. So just before we go, an important thing to remember is now, since we are dealing with 6 nodes, that is 12 degrees of freedom, our force, displacement, and elements of these equations will be connected by, of course, the force matrix, if you can remember, which would have now, each node would have 2 forces, which will go up to X direction, the force of the 6th node at the 6th node in the Y direction. So this will be a 12 by 1 matrix, which is related to the displacement matrix U1, V1, or V6, U6, V6. Again, a 12 by 1 matrix, displacement functions, and these are related via the element stiffness matrix, which is nothing but a 12 by 12 matrix, because we have 12 degrees of freedom. So K11 will go up to K112. Similarly, K21, K31 will go up to K121. The very last element would be K1212. So just to give you a feeling as to what type of matrices that we are tackling. By now, I think you have not lost hope in performing a hand calculation, trying to motivate you as to why we exactly use softwares to calculate these problems.